Data structures are fundamental to computer science and programming. They provide a way to organize and store data in a computer's memory, enabling efficient access, manipulation, and processing. Just as a well-organized library allows for quick book retrieval, efficient data structures are crucial for building fast and scalable software applications. Imagine searching for a specific book in a library with millions of volumes, but no organizational system. It would be a daunting and time-consuming task. Similarly, without data structures, computers would struggle to handle the vast amounts of data they process daily. Data structures provide the framework for organizing data, making it easy to locate, update, and retrieve information quickly. The choice of data structure directly impacts the performance of algorithms. Algorithms are step-by-step procedures for solving problems, and they rely heavily on how data is structured. An algorithm designed for a sorted array, for example, will be significantly faster than the same algorithm applied to an unsorted list. Understanding data structures is essential for any programmer looking to write efficient and scalable code. By selecting the appropriate data structure for a given task, developers can optimize their programs to run faster, use less memory, and handle larger datasets. This efficiency is crucial in today's world, where applications need to process massive amounts of information quickly and reliably. Primitive data structures are the most basic data types found in programming languages. They serve as the building blocks for more complex data structures and are directly supported by the computer's hardware. These data types represent single values and include integers, floating point numbers, characters, and booleans. Integers represent whole numbers, both positive and negative, without any decimal points. They are used for counting and performing arithmetic operations. Floating point numbers, on the other hand, represent numbers with decimal points, allowing for greater precision in calculations. Characters represent letters, symbols, and digits used in text. They are stored as numerical codes, such as ASCII or Unicode, which map each character to a unique number. Booleans represent truth values, either true or false, and are used in logical operations and decision-making within programs. Primitive data structures are essential for representing simple data elements. However, for more complex applications, we need ways to organize and store collections of data. This is where more sophisticated data structures, such as arrays, linked lists, trees, and graphs, come into play. These structures provide mechanisms for storing multiple data elements and defining relationships between them. Linear data structures organize data elements in a sequential manner, where each element has a defined predecessor and successor, except for the first and last elements. Two common types of linear data structures are arrays and linked lists, each with its own advantages and disadvantages. Arrays are collections of elements stored contiguously in memory. This contiguous allocation allows for direct access to any element using its index, making retrievals very efficient. However, inserting or deleting elements in an array can be inefficient, as it may require shifting subsequent elements to accommodate the change. Linked lists, on the other hand, store elements in nodes, where each node contains the data element and a pointer to the next node in the sequence. Unlike arrays, linked lists do not require contiguous memory allocation, making insertions and deletions more efficient. However, accessing an element in a linked list requires traversing the list from the beginning until the desired element is found. The choice between an array and a linked list depends on the specific application requirements. If frequent insertions and deletions are expected, a linked list might be a better choice. Conversely, if fast access to elements is crucial, an array would be more suitable. Non-linear data structures, unlike linear ones, do not organize data in a sequential manner. Instead, they represent data elements and their relationships in a hierarchical or network-like structure. Two prominent examples of non-linear data structures are trees and graphs. Trees, as the name suggests, organize data in a hierarchical structure resembling an upside-down tree. Each element in a tree is called a node, with the topmost node called the root. Nodes can have child nodes, forming branches and subtrees. Trees are widely used for representing hierarchical relationships, such as file systems and organization charts. Graphs, on the other hand, represent data elements as vertices connected by edges. These edges can be directed or undirected, representing relationships or connections between the vertices. Graphs are versatile structures used in various applications, including social networks, transportation systems, and recommendation engines. Nonlinear data structures provide efficient ways to represent complex relationships and solve problems that are difficult to handle with linear structures. Trees, for instance, enable efficient searching and sorting algorithms, while graphs are well suited for modeling networks and finding optimal paths. Data structures are not merely containers for storing data. They also support various operations that allow us to manipulate and retrieve information efficiently. Some common operations performed on data structures include insertion, deletion, searching, sorting, and updating. Insertion involves adding a new data element to a data structure. The efficiency of insertion depends on the type of data structure and the position where the element is being inserted. For example, inserting at the end of an array is generally faster than inserting at the beginning. Deletion involves removing a data element from a data structure. Similar to insertion, the efficiency of deletion varies depending on the data structure and the position of the element being deleted. Searching involves finding a specific data element within a data structure. Different search algorithms are available, with their efficiency depending on factors such as whether the data is sorted or not. Sorting involves arranging the data elements in a specific order, such as ascending or descending. Sorting algorithms are crucial for tasks like searching, finding duplicates, and presenting data in a meaningful way. Updating involves modifying the value of an existing data element within a data structure. The efficiency of updating depends on the data structure and how easily the desired element can be accessed. Selecting the appropriate data structure is paramount for designing efficient and scalable algorithms. The choice depends on various factors, including the type of data being stored, the operations that need to be performed, and the performance requirements of the application. For instance, if the data needs to be accessed sequentially and insertions or deletions are frequent, a linked list might be a suitable choice. On the other hand, if random access to elements is crucial and the size of the data is fixed, an array would be more appropriate. Trees are excellent for representing hierarchical relationships and supporting efficient searching and sorting operations. Graphs, with their ability to represent complex relationships between data elements, are well suited for applications involving networks, such as social networks and transportation systems. Understanding the strengths and weaknesses of different data structures is crucial for making informed decisions during the design phase of software development. Choosing the wrong data structure can lead to inefficient algorithms, slow performance, and increased memory usage. Section 7. Algorithms and Data Structures. Algorithms and data structures are inextricably linked. An algorithm's efficiency heavily relies on the chosen data structure, as the way data is organized directly impacts how quickly operations can be performed. In essence, data structures provide the foundation upon which algorithms operate. Consider the task of searching for a specific book in a library. If the library uses a simple data structure like an unsorted list, the search algorithm would involve checking each book one by one until the desired title is found. This approach, known as linear search, can be highly inefficient for large libraries. However, if the library uses a more sophisticated data structure like a binary search tree, where books are organized based on their titles, the search algorithm can be optimized significantly. Binary search allows for logarithmic time complexity, meaning the search time increases proportionally to the logarithm of the data size. This example highlights the importance of selecting the right data structure to optimize algorithm performance. By understanding the strengths and weaknesses of different data structures, programmers can choose the most efficient way to organize data for a given task and design algorithms that leverage the chosen structure's advantages. Section 8. Real-world applications. Data structures are ubiquitous in computer science and have countless real-world applications. From the apps we use on our smartphones to the complex systems powering global financial markets, data structures are essential for managing and processing information efficiently. One prominent example is search engines like Google. These engines rely heavily on data structures like inverted indexes, which allow for fast retrieval of web pages relevant to a user's search query. Inverted indexes map keywords to lists of documents containing those keywords, enabling efficient searching across billions of web pages. Social media platforms like Facebook and Twitter utilize graphs to represent users and their connections. These social graphs capture relationships between users, enabling features like friend suggestions, newsfeed personalization, and targeted advertising. E-commerce websites like Amazon employ recommendation systems powered by data structures like collaborative filtering algorithms. These algorithms analyze user purchase history and preferences to recommend products that are likely to be of interest, enhancing user experience and driving sales. These are just a few examples of how data structures are used in real-world applications. Their versatility and efficiency make them indispensable tools for solving a wide range of problems across various domains. Section 9. The future of data structures. As technology continues to advance and the amount of data generated globally grows exponentially, the importance of efficient data structures will only become more pronounced. New challenges and opportunities are emerging, driving innovation in the field of data structures. One area of active research is the development of data structures optimized for modern hardware architectures, such as multi-core processors and cloud computing environments. Traditional data structures, designed for single-threaded execution, may not fully leverage the capabilities of these parallel processing systems. Another focus is on designing data structures that can handle the increasing volume and complexity of data generated by modern applications. This includes developing structures that can efficiently store and process unstructured data, such as text, images, and videos. Furthermore, there is growing interest in data structures that prioritize privacy and security. As data breaches and privacy concerns become more prevalent, researchers are exploring ways to design data structures that protect sensitive information while still allowing for efficient processing and analysis. Section 10. Conclusion. The power of efficient organization. Data structures are the backbone of efficient programming and play a pivotal role in shaping the performance and scalability of software applications. From primitive data types to complex nonlinear structures, choosing the right data structure for a given task is crucial for optimizing algorithms and handling data effectively. Understanding the principles of data structures empowers programmers to make informed decisions during the design phase of software development. By selecting the appropriate data structure, developers can ensure their programs run faster, use resources more efficiently, and handle larger datasets with ease. As technology advances and the amount of data we generate continues to grow, the importance of efficient data organization and processing will only become more paramount. By mastering the concepts of data structures, programmers can build robust and scalable applications that meet the demands of our increasingly data-driven world.